Good morning, everyone. Happy Tuesday. Still got people coming in.
Morning.
Good morning.
Good morning.
All right, we got 19 students in here. Oh, numbers are getting worse. All right, so last time we more or less completed chapter 14. Of course, if you go over my YouTube channel, which I did update the list of videos on that. So if you look into my, important documents and links, there's a text document that has my YouTube channel videos. It's just a list of the name of the video, followed by whether it's relevant for calculus-based physics, conceptual physics, or algebraic physics. And then it's got the actual URL for the YouTube channel link to that particular video. So you can check that to look for things. But basically, you should be well in a good position anyways to finish any chapter 14 related stuff. Chapter 15, I'm going to knock out today. It's not a lot of super hard stuff. It's pretty straightforward, but I'm going to give you basically the rundown on what happens with waves, the equations that we use for waves, specifically a plane wave and stuff like that. So it turns out the wave equation has a very specific form, which I've mentioned before. You can see that if you want to look at some of my Maxwell equations videos that you see in the YouTube channel, you can see some examples of it. And the wave actually has a very specific location for the actual velocity in the wave equation. So when Maxwell put his 4 equations together, he came up with 2 wave equations, which I do in my YouTube channel video on Maxwell's waves as well. And at that instant, it was obvious to him what was actually doing the waving in light. In other words, he knew what light was. Light was an electric field oscillating in one plane, a magnetic field oscillating in a perpendicular plane, and a third mutually perpendicular direction was the direction in which they were going, such that if you stick your index finger in the direction of the electric field, stick your middle finger in the direction of the magnetic field, then your thumb points in the direction that the wave's actually going. So this is the electric field, magnetic field, and the wave's going. So if the wave is vertically polarized, then that means the electric field is vertical, like you see it sort of right now. Well, that's vertical. The magnetic field is when the electric field's up, the magnetic field would be to my right. I think that might be to your left, and the wave would be coming towards you. Okay, all of that stuff you can get from Maxwell's equations. But it was kind of interesting that because it came into that natural form, he found that the spot where the velocity was a product of epsilon 0 times mu 0, epsilon 0 being the permittivity of free space and mu 0 being the permeability of free space. And if you multiply those two, then take the reciprocal and then take the square root, lo and behold, you got the speed of light. And he was like, whoa, well, this I know what light is. So that's kind of cool. So I've also seen the MCAT or seen versions of the MCAT, and I've been once was contracted to write a series of problems to help people with the physics part of the MCAT, and also I forget the name of it, but there's like an LSAT or something like that. That's the test that you take if you want to become a lawyer. So I know that I've seen certain physics questions in those realms as well. So I'm going to try to expose you to some of those things instead of just the typical things that come in our chapters. So one of the things that we talk about is waves and when they interact. And one of the things I've seen on many MCAT tests is you take and you shake a rope, okay? That causes a wave, and that wave is going to go through space. Now, when the vibrating is perpendicular to the direction it travels, or the propagation, that's the word we use for a wave traveling. When the vibration is perpendicular to the propagation, that's called a transverse wave, okay? Transverse wave. And you can tell, sort of looking at the ocean, that ocean waves look like transverse waves. In other words, you see the rising of the water, which is what the oscillation is. You see the rising of the water vertically while the wave is actually traveling horizontally. It turns out the ocean waves are actually a little bit transverse and a little bit longitudinal. That's why I'm sort of hedging my wording here. Sound waves, on the other hand, sound waves occur, you can imagine like the diaphragm of a speaker. That's the little center part that does all this in the speaker. What it does is it will basically get some voltage through a magnet. That magnet will cause this diaphragm to shoot out this way. When it does, it takes all the little molecules that's in its way and pushes them up against each other. And because they now have some momentum, those molecules are going to travel out away from the speaker, but they're going to have this area where the molecules are really tightly packed. Then when the next note comes, the magnet releases and the diaphragm falls back, and that leaves an area where there's less molecules per unit volume, and that area is called a rarefaction. This front area is called a compaction or compression, where the molecules are pushed together really well, and this other one's called a rarefaction. It's not a misspeak. It's RAREFACTION. Your book just stopped using that terminology, but I know they're still using that terminology in ultrasound physics. So they're just using expansion in your textbook, but it's compression and rarefaction, or compaction and rarefaction is another way of saying it. In that case, what you see is the compression is going this way, and the rarefaction, of course, is going this way, but the wave is also traveling this way. So that's called a longitudinal wave. Other things have both longitudinal and transverse components than just ocean waves. And the way you can tell an ocean wave does is if you swim out, let's say at least past the first sandbar, preferably past the second, which you're starting to get in the area where it could be potentially problematic if you're not a good swimmer. If you wear a life jacket, that would be probably smart. But anyways, when you're out in the ocean, you're just sitting there and there's a wave way over here coming towards you. What you'll feel is as the wave gets closer to you, you'll feel yourself be pulled down towards the wave. That's the longitudinal component, the towards the wave part is. And you'll also go down, and then as the wave passes you, you'll go up and then come back down and drift forward. What's happening is you're going and making a little circle. The vertical part of that circle is the transverse part of the wave, and the forward backwards part of that circle is the longitudinal part of the wave. So that's how you can tell that ocean waves are both longitudinal and transverse. If you happen to be lucky enough to do it somewhere or some particular day where the water is really crystal clear, you can spot something on the bottom as you're swimming, say 6, 7, 8 foot of water. You can see the bottom, and you'll see that you literally move out to sea, and then you lift up and come towards the shore, and then you sink down and go back towards the sea. So you can see that you're actually making a circle as you go by. That's a case in point. Earthquakes, for instance, also have a longitudinal and a transverse part. The transverse part is called the P wave, and the the transverse part is called the S wave, and the longitudinal part is called the P wave. And the transverse part, it sounds weird, but it can't propagate through the liquid portion of our core of our Earth. And you say, well, why is that? We see ocean waves are partly transverse, so why can't it? Well, that's the ocean wave that's occurring on the surface of the ocean, and the surface of the ocean is a asymmetric situation. So let's let this represent the horizon. So above is the sky and below is the water. On this top layer, it's not symmetric because below and to the right, below and to the left, below and to further to the left, below and to further to the right. All those molecules of water are all pulling downward on that molecule. And the ones to the left of it and to the right of it are pulling to the left and to the right, right? So the surface molecules of water have something called surface tension that tries to keep all that water together. So when this molecule lifts up, when a wave comes by, the attraction between that molecule and the molecule to the left of it causes the left molecule to lift up. So you can do like that, sort of like a wave in a football stadium. that is a transverse wave on the surface of the water. Now, what I'm saying is you can't get a transverse wave to go underwater through the water, because when you're underwater, there's a molecule here that you might want to make the transverse wave, but there's a molecule here and here, this one pulling up, this one pulling down, this one pulling left, this one pulling right. All of those cancel each other out. So if this molecule tries to lift up, it's going to say, okay, go for it. And this molecule next to us is going to go, whatever, right? So that's why S waves, which are transverse waves, can't actually travel through the liquid part of our core. And we've used that with various detectors all over the surface of the Earth to map out what the inner parts of our core of our Earth, or the inner parts in general of our Earth, are, because they travel at different speeds through different materials. And that's part of what we're going to learn today. So first off, I want to show you some of the basics. Now, I've given you sort of the rigmarole on it. Let me first show you what the equation for a wave is. In general, the equation for a wave is a second order derivative of something. I'm going to call that something the phi, and that something is the thing that's oscillating. So in the case of the electric field, it's the electric field going this way up and down while it travels that way. In the case of a pressure wave, it's the density of the air pressure, and it's going this way and this way while it's traveling this way. So this thing could be density, it could be pressure, it could be electric field, but it's a second derivative with respect to space. And in fact, it could be x, y, and z, in which case you have a d2 phi over dx squared plus a d2 phi over dy squared plus a d2 phi over dz squared. But since phi would then be a function of x, y, and z, these would have to be partial derivatives, which we write this way. Okay, so it'd be partial plus partial plus the partial. So that's what it would be in 3 dimensions, is that. In 1 dimension, we can just call it this, and then it's equal to the second derivative of the same thing, but this time with respect to time. And you see, if you multiplied this by 1 over velocity, then the meters would end up in the bottom and the seconds would end up in the top. So it turns out that 1 over v squared has to go in there just to make the units work. So that is the form of a wave equation. If you ever have something that is a second derivative in space equal to some number times the second derivative in time, then that's going to be a wave equation, no ifs, ands, or buts about it. And a solution to this is called a plane wave. And this is also of the form, you can write it this way. You can say d2 phi over dt squared minus 1 over v squared d phi, d2 phi over dx squared, something like that, equals 0. You can write it that way as well. And what you see here is this is a string of derivatives that have constant coefficients. You know, a number is a coefficient, and such equations are satisfied by equations whose derivatives repeat themselves. So if you take the derivative of a function and you get that same function back, then that is a candidate solution for this. So we use phi as an ensatz solution. In other words, when we're solving these types of equations, and one of which is the wave equation, another one is d2x over dt squared plus b over m dx over dt plus k over m x is equal to 0. That's another equation where you have multiple derivatives multiplied by constant coefficients. You'd again use an ensatz solution such that d phi over d whatever is actually, let me write this better. D phi over dx is equal to something times phi, and d2 phi over dx squared is also equal to something squared times phi, something like that. When you have this type of function, then it's going to automatically satisfy the differential equation. You'll just get some algebraic constraints on parts of the function. So can anybody think of a function that you take a derivative of and it gives you back like some number times that same function?
An exponential function, like e to the exponent of some function of x.
Exactly, and that's the more typical one that we use. And the reason why we normally typically use that is we say phi is equal to, let's say, some constant a times e to the rho x. That's a very typical solution. It's a little bothersome for people because they don't, you're thinking of a wave, so you think of sines and cosines. Well, the derivative of sine is fine, but as you'll notice, it comes out as a cosine times something. But the second derivative comes back to the original function. So if you take also, you can take phi is equal to a1 sine some function of x and t plus a2 cosine of some function of x and t. If you do that, that does the same thing, because notice the first derivative is going to turn this into some number times a cosine, and it's going to turn this into some number times a sine. So you're basically getting back to the same function, a sine plus a cosine. So these are two ensatz solutions for these types of equations. Well, it turns out that you can use either one. The only deal is if you want to use this one and get the sine out of it, you've got to realize Euler's formula, and that's e to the I theta is equal to cosine theta plus I times the sine of theta. So that's an identity. Obviously, if you replace that with e to the negative I theta, where that's a negative, you get cosine theta minus I times the sine of theta. So when you're all said and done and you've solved for this rho, then you can go back and say, well, if I want to make it a cosine, then I just make this e to the rho x equal to cosine rho times x plus I times the sine of rho times x, and you can get back to something like that. So that works as well. So those are real solutions. And in fact, it turns out that if you use f of x and t equal to kx minus omega t, or ky minus omega t, or kz minus omega t, or more generally, you could just do k vector dotted with r vector, where r is the position vector, x I hat plus y j hat plus z k hat minus omega t, then that works as well. Okay, so generally what we'll say is a plane wave can be equal to y equals a sine k dot r minus omega t. And if you want to keep it as a sine, then you have to add a phase constant plus phi, which I'll say plus alpha, say. And that's just an arbitrary constant that you can set using the initial conditions to make sure it's the right phase, because, when you start studying it, the initial time could be such that the position is 0 at t equals 0, and you get a real sine wave. But you could also have a scenario where the initial velocity was not 0, but the initial position was, or something like that, and then you could get something that looks like this instead. Or you could have something in between, in which case it would look something like, let's say, this. If that's the case, then you're having a phi that is somewhere between pi over 2 and 0, right? So this will be pi equals pi, or excuse me, alpha equals pi over 2. This one will be alpha equals 0. And then this one will be something in between those two things, right? So by allowing this phi in here, you're allowing this function, if it was sine, which would look just like the black line, you're allowing that to shift left and right. Alternatively, you can just use y equals a1 sine k dot r minus omega t plus a2 cosine k dot r minus omega t. Okay, that's called a plane wave. And what we mean is there exists a plane, a two-dimensional structure, such that the amplitude of this wave is a constant. So in other words, what you'd look at is if you had, let's say it's going in the Z direction, okay, then Y would be out here and X would be here. Whoa, X would be here. And what you get generally is, say, a function that looks like this. Right? But in a plane, that's going to be a constant. So this comes all the way back over here.
It's off screen.
Oh, thank you. This comes all the way back over here and then comes back down like this. Then comes back down up like this. And then comes back down like this. And then comes back down up like this. So you can see this is sort of like that. So you see along this plane, by the way, everything's constant. The X is a constant, or in this case, since we actually graphed Y, I should have put Y up there. Sorry about that. Then I just have to put X back here. So let's do that. Let's do this as Y. And this is X. So you can see everywhere along this plane, that is the XY plane, the wave has a constant value. So this line right here forms a plane that's perpendicular to the Z axis. And this function that I actually chose to graph was Y equals A1 sine KZ minus omega t plus A2 cosine KZ minus omega t. That's the plane wave. Obviously, like I said, you can play around with the constants and a possible phase angle like this. And if you do that, then you could actually get it just represented as a sine kz minus at, or as a cosine kz minus omega t. So just know that all of these are potential solutions. In fact, it turns out these equations, which are linear equations, in fact, have this property that if you find one solution and then you find a second solution, if those two solutions are linearly independent, which means the only way you can multiply each one by a different constant and get zero is if the two constants are zero, then those two solutions added together and multiplied by separate constants is the more general solution. So a second order equation would have two of them, a third order equation would have four of them, a fifth order equation would have five of them. So in this case, sine and cosine are linearly independent. So a second order equation could be written by this. We found that sine was one solution. We found that cosine was one solution. So any linear combination will also be a solution. And if you get all the linear combinations, then it's the general solution. And obviously all of them only requires two. So you could use a constant times sine plus a constant times cosine, and that's the general solution. Does that make sense? You'll learn more about this in differential equations, but the main thing is just know this is the form of a plane wave. And that's what I mean by a plane is there exists a plane. Often it's perpendicular to the direction of travel, but it doesn't have to be. A longitudinal wave wouldn't have that as the case. But the value of the amplitude of the wave is a constant on a particular plane. And then that plane is actually moving with a certain velocity, which you can see by basically the boundary conditions that are applied to this. So let's take this one case. Let's take y equals a sine kz minus omega t plus alpha. I'm going to take that as a solution, and I'm going to plug that into the wave equation up here. So I'm going to say my wave equation is in fact d2y over dz squared equals 1 over v squared times d2y over dt squared. That's the wave equation. And you can now see the general form: derivative in space, derivative in time, separated by 1 over v squared. So if I take the first derivative, dy dx.
Could you actually bring that closer? It's pretty blurry.
That stinks. I'm hating that it's getting blurry like that because it looks really good on this side. Must be a bandwidth issue. And I think that means the tape's going to be crap. the recording is going to be crap. So anyway, so that's dy dx is equal to, hear my words here, that'll help you as well. When I take the derivative of this function with respect to, actually I said x, it should be z. When I take the derivative of this with respect to z, it'll be the derivative of sine u with respect to u times the derivative of u with respect to z. So the derivative of sine u is just cosine u. And u, of course, is kz minus omega t plus alpha, sorry. That's a plus alpha there. I know it looks like crap, but anyways. I love this thing my daughter gave me. Okay, now if you take the second derivative of this, oh yeah, by the way, I got to take the derivative of this with respect to z, and the derivative of this with respect to z is just k. So I got ka cosine kz minus omega t plus alpha. If I say take the second derivative of this with respect to z, then I get k squared. Derivative of cosine is actually negative sine, so it's going to be negative k squared a sine kz minus omega t plus alpha. Now I got to do the same thing with the derivative in time. Dy over dt is equal to, in this case, notice the derivative of u with respect to t is a negative omega. So I'm going to get negative omega a cosine kz minus omega t plus alpha. And then d2y over dt squared is going to bring in another negative. And this time I'm taking the derivative of cosine, so that I get yet another negative. So I'm going to get a negative and a negative, which would make a positive, but then I get a third negative, and that's going to make it a negative, I think. So it'll be omega squared a times sine of kz minus omega t plus alpha again. So let me double check that. I had a negative. I take the derivative of cosine, I get negative sine, that makes a plus. And then I take the derivative of negative omega t with respect to t, and I get another negative. So yeah, that should actually be a negative. Everybody agree with me on that? So now all we have to do is just plug these two things into that. So on the left-hand side, I get negative k squared a sine, and I'll leave the argument off. Because why write it? We know what it's in there. It's kz minus omega t plus alpha is equal to 1 over v squared times negative omega squared a sine again of whatever that crap is. So this has to be true for all x, or excuse me, all z. This, damn, I gotta get used to being able to actually physically erase. So it's got to be true for all z and t. Okay, so that means we can basically consider the case where sine of all that junk is not 0, and we can just add negative k squared is equal to, or negative k squared minus 1 over v squared times negative omega squared. Actually, I'll bring that over to this side. Yeah, that's cool. All that times a sine blah blah is equal to 0. So in order for this to be true at all times, this thing has to be 0. This little part right here has to be 0. So we get negative k squared plus omega squared over v squared is equal to 0. So that means that v must be equal to the square root of omega squared over k squared, which equals omega over k. So v is equal to omega over k. So as long as v is equal to omega over k, then this is in fact a solution of the wave equation. Okay. all you have to do to evaluate the alpha and the A is you've got to be given, usually they give you y of t equals 0 is equal to y0. And usually they give you y of z equal to 0 is equal to y sub z0. In other words, they'll give you a z and a t equal to 0 and give you what the y is in that case, and that gives you two equations. Those two equations are enough to evaluate the a and the alpha. Okay, so that's really how you solve these equations. But now that you have that little background of what equations waves satisfy and know how to actually evaluate the constants, I need to tell you some fundamental ideas about waves. So one thing is you can start a wave by just taking a piece of rope. Let's say this is rope. And I'm going to do something kind of neat. I'm first going to attach it to a wall. Okay, so it's attached to a wall. It can't move up and down. And what happens when you give that a shake like this is that wave will propagate along that rope this way. And as it gets closer and closer and closer in the future, when it gets right here, that tension in the rope is going to try to lift up on that ring that's mounted to the wall. That's going to actually cause Newton's third law to kick in. And Newton's third law says that when I apply a force in the upward direction to that ring, the ring's going to apply a force in the negative direction to the rope. So that wave will come out upside down and go back this way, so that later it'll look like this, and then later it'll look like this, and so on and so forth. So that's how a wave actually propagates in time along a rope. Okay, if that end is mounted, it's going to bounce back and come back upside down. That's one of the conceptual questions that I've seen literally on the MCAT. So people that are interested in med school and law school, those are tests. The MCAT and whatever that legal test is are ones that have asked this in the past. So it's not bad to know. The other neat thing about this is if you send them out at just the right rate, so that the instant you send a wave, your hand goes down, and then it can follow through and make this downward wave at just the right instant, then you'll get what's called a standing wave pattern on here. And a standing wave pattern, in the case where one end's free and the other end's not, so we mount it this way. This is a free end, which implies an antinode. What we can get is a standing wave that looks like this, where the length of the string, L, is equal to a quarter of a wavelength. Okay. Remember, a wavelength is basically this typical scenario. That's a wavelength, right? So you can see this just goes from here to here. That's a quarter wavelength. If you shake it a little more frequently, then you might even be able to get it to do this, in which case that's 3/4 of a wavelength. Okay.
Can you bring it closer so I can see the writing?
Yes. And now I didn't draw that blue purple one very well, but basically it's 3/4 of the distance along the sine curve. So it's up to this next peak.
And that's like a lambda?
That lambda is the total wavelength. Remember, the wavelength is this distance from midline, skip one, to midline. So what I'm showing you for standing wave, for one end free and one end locked, which by the way, this is called a node. just like that end was called an antinode. At this point, we get two nodes. We get that node and this node, but in the pink case, we only got one node, and that was here and here. We can add yet another node, and then you'll get, instead of this curve, you'll get a whole wave plus a quarter. So I would say roughly here is a whole wave and then a quarter. So yeah, I could do in principle and then I repeat that upside down. And in that case, L is equal to 5 lambda over 4. I'll write it bigger because that didn't come out so well. And plus this pin's dead, so I need to get rid of that. So you can go on. In that case, I actually have 1, 2, 3 nodes, and that gave me 5 lambda over 4 is the wavelength, is the actual length of the string. Those are standing waves. That's what happens when you get in sync with sending waves out at just the right rate where they come back to you, and you feed it and feed it and feed it. If you do it at one frequency, you get this standing wave. If you do it at a higher frequency, which means a shorter wavelength, of course, you get this one. And then if you do it at a higher frequency still, you'll get the black one. And you can keep on going on and on and on. And I think you see it's 1 lambda over 2, 2 lambda, or excuse me, 1 lambda over 4, 2 lambda over, or excuse me, 3 lambda over 4, 5 lambda over 4. So really it is L is equal to N, I'll write N sub O, lambda over 4, where N sub O are the odd numbers, 1, 3, 5, 7, ... Those are all the standing waves you can get like this. This is in fact sort of like a organ. If you're playing an organ that has just an open end like that, then that's the standing wave patterns you'll get. You'll get a quarter wave, you'll get a 3/4 wave, you'll get a 5/4 wave, so on and so forth. If you had another scenario though, let's say you had a wall and another wall, so the ends are actually both nodes, then you can get this one. This is L again. You get L is equal to, in this case, lambda over 2. You could also get, in this case, L is equal to 2 lambda over 2. And you could get even going to a third roughly. I'll do this one in black. You get L is equal to 3 lambda over 2. So in this case, L is equal to N lambda over 2, where N is equal to 1, 2, 3, ... So that's another case of standing waves. But in this case, you have the 2 ends are nodes. You can also have the 2 ends being antinodes. You can have one end being an antinode or the other end being an antinode. I showed you one end being an antinode. If the other end was, it'd be the same thing, but pointing that way, and so on and so forth. But by doing this, you've now found all the harmonics, if you will, of the wave. So basically, this lowest frequency part is the fundamental frequency. So when you pluck a guitar string, you're actually supposed, since a guitar string, notice, has a fret at both ends. It's got the bridge as well as the fret at the very end. So when you pluck a string, the fundamental note is that guy. So if you measure the length from where the chords start now by the hole in the guitar, let's say the guitar looks like this, and then you got this and this, okay. Basically, and you also have no, that's pretty much it. So you have a string right here. If you pluck that such that it makes a half a wavelength, so you literally measure that distance from there to there, or if you fret it, maybe you put your finger on it here so that you can fret it here. If you measure that length right there, that will be the wavelength of the wave. you can then know what the frequency is supposed to be, and you can use V is equal to F times lambda. You know the frequency because that's what you tune it to, like 200 and what is it, 256 is C, 256 hertz, I think is C. So you can put 256 there. You could measure that wavelength, and from that calculate the speed of the wave. And what that speed will turn out to be is something like the square root of something force related over something mass related. Okay, that is the fundamental velocity of mechanical things. It's some force relation. So now that you know all this stuff and all these fundamental frequencies, and of course the first harmonic would be the fundamental frequency for this one is this guy, where L is equal to lambda over 2. The first harmonic would be L equals 2 lambda over 2. The second harmonic would be L equals 3 lambda over 2, and so on and so forth. So you call them F0, F1, F2, so on and so forth. And they are really just, another octave up. So if you're thinking about music, you go from a C to the next C, and you go from a C to the next C, and so on and so forth. That's what's going on there. Now, when you actually apply this wave equation to work out, for instance, the velocity of a wave on a string, so let's say wave on a string.
Quick question.
Yes.
What does it say in the square root?
It says force and mass.
Force over mass. Okay.
Yeah, and you'll see this example will make sense of that. So when you do the derivation for a force on a string, and I usually do this, but I'm not doing it this time because you can see it in your book. What you find out is that it's got to be the tension in the string. So that's the force part I was talking about, over mu, which is the mass per unit length. So, if you look at guitar strings, there's a fat one, and then there's a really thin one, and then all the other ones are in between. Well, that fat one would have a large mass per unit length, which means the velocity is going to be kind of slow compared for a given tension. That doesn't mean you necessarily put all the tensions the same for each of the 6 strings or 4 strings if you're talking about a bass guitar. But whatever tension it is, if you set the tension constant, then the velocity of the wave for the fat string would be lower than the velocity of the wave for the skinny string. And of course, that velocity is always going to be equal to the square root of the tension of the string divided by the mass per unit length. And then, of course, you can use the length to be the distance from here to this fret, or to actually one of the frets. I can't remember if this, we call it the nub on the banjo. I don't know what you're calling it on a guitar. But these little lines in here are frets, and you can fret the string to make its length shorter. And that helps you understand, because for a given string, the velocity is a constant, because you're not going to change the string and you're not going to change the tension while you're playing the note, right? So this is going to be a constant. So if I move my finger down the fret, the wavelength is getting smaller, so the frequency must be getting, it's got to maintain a constant velocity. So if I move my finger down to a lower and lower fret, the wavelength is getting smaller. What must the frequency be doing to compensate for that?
Increasing.
Increasing. So that's why you get a higher note when you put your finger down here, say, than when you have no finger on it at all, or even compared to your finger being here. Okay. So all velocities, wave velocities, are always something about force divided by something about inertia. So that was the transverse wave on a string. There also turns out to be a velocity of a longitudinal wave. So longitudinal wave, that velocity is actually equal to the square root of the bulk modulus.
It's off screen.
Sorry, thank you. That velocity is equal to the elastic force factor divided by the inertia factor, which turns out to be E over rho, where that E is in fact the elastic modulus. those moduli are basically a pressure divided by a distortion. That's what the modulus is. And there's a chapter on it that you can, there's a chapter on strength of materials, more or less, that talks about these various moduli. This is actually just the density. And another way of expressing it is you could say for a wave traveling in a liquid or a gas, so in a liquid, notice I said in a liquid, then the velocity is equal to the square root of the bulk modulus divided by rho.
Can you bring that closer so you can see it?
Yes. Okay. And I was talking earlier about the American Forest Products, or the Wood Products Association of America, that puts out those prints for me doing structural engineering work. And they actually give you these moduli for the various types of wood and stuff like that. Obviously, you could talk about a wave going through a 2x4 by hitting one end of the 2x4 with a hammer. And of course, that will cause a longitudinal wave that looks like this, basically. Right. So now you've got a velocity that's related again to something like a force divided by something like an inertia, such that the square root of it has units of mass per second, or excuse me, meters per second. And then you'll have the velocity, but the velocity is always equal to frequency times wavelength. And the reason that is you can look at it this way. We said velocity was equal to, from our differential equation, we found that the velocity was equal to omega over k. Well, k is defined to be 2 pi over the wavelength, and omega is defined to be 2 pi times the frequency. So you can see if I put 2 pi f there and 2 pi over lambda there, I end up getting f times lambda. So you can see V equals omega over K is the same thing as V equals F over lambda. Okay, so that's where all that junk came from. Now you know how to treat all that. You can actually say, okay, well, if I know, for instance, the fundamental frequency, I know how to get the second frequency if, for instance, it's got two nodes, a node on each end. For a node on each end, the wavelength is in fact 2 times the length over n. N equals 1 corresponds to lambda equals 2L over 1. So lambda is twice the length of the string. For lambda, for the first fundamental, we see that now it's going to be 2L over 2, which is just L. So for the first fundamental, the string will be the entire, or the note or the wavelength will be the entire length of the string. For F3, or excuse me, F2 in this case, then it's going to be 2L over 3. I'm just solving this equation for lambda, in other words. And from that, you can then say, okay, well, just by knowing one of the frequencies, I can immediately get what all the other frequencies are just by using this relationship if it's got a node on each end, or this relationship, which I gave you here, if it's got a node on one end. Now, that gives you the mechanics of the waves. It tells you how to get one frequency, find a fundamental frequency, plus it also tells you how to find each of the harmonics. And with that, you can also now talk about the energy supplied by the wave. And when you do that, it turns out that the energy, if you take as the model, E is equal to 1/2 Ka squared, right? Well, Ka squared, if you remember correctly, that's actually equal to that wave equation, and that wave equation for the plane wave, of course, was y equals a sine kx omega t. Well, when you start plugging all that junk in, you can actually get that it's equal to 2 pi squared times the mass that the object had times the frequency the object had times the amplitude the object had. Okay, that's a really big deal. That means the energy of a wave is proportional to the square of the frequency and is proportional to the square of the amplitude. So if you're at the ocean and you look and a 2-foot wave is not that big a deal. And you think, okay, well, a 4-foot wave shouldn't be much bigger. What you got to realize is a 4-foot wave is going to have, in fact, 4 times as much energy as a 2-foot wave. If you compare a 1-foot wave to a 3-foot wave, then the 3-foot wave is going to have 9 times as much energy as the 1-foot wave. A 4-foot wave would have 16 times as much as the 1-foot wave. A 5-foot wave would have 25 times as much. But it also depends on the frequency. So if the waves are coming in very rapidly, 1 wave, 2 wave, 3 wave, 4 wave, like that, that's a higher frequency. And this frequency, the energy is related to the square of the frequency as well. So that's what really dictates a wave. And it turns out that the intensity of a wave, which is really the power divided by the surface area. So power, and that's joules per second, like watts, divided by the surface area. Then that's just P over S. Okay, that's the intensity of a wave. It turns out that that intensity of a wave, I, is inversely proportional to the distance squared. So as that wave gets farther and farther away, basically the surface area is increasing as well. So if you double the radius of the sphere that the wave is propagating out at, then it goes from a 4 pi times 1 squared surface area, but now it's going to be distributed over a 4 pi times 2 squared, or 4 times as much. So going from 1 meter away to 2 meters away decreases I by a factor of 4. Okay, it doesn't subtract. I want to know that that is decreasing by a factor of 4. So you can actually use that to say, okay, well, if an earthquake hit here and had a intensity of this at 1 mile away, if I'm 10 miles away, how intense will my wave be? Well, that'll be 100 less, because 10 times 1 is how you get 10 from 1. And if you square 10, you get 100. So the intensity will fall by 100. That's pretty much how you treat all these waves. And you can see like a left-going wave would be kx minus omega t, and a right traveling wave would be, a right traveling wave, one going in the positive direction, is kz minus omega t. So let me write that rule down just so everybody knows. So kz minus omega t implies positive z direction, and a kz plus omega t means a negative direction. Of course, if you had a kx instead of a kz, then it'd be the x direction instead of the z direction, and so on and so forth. So those are things to remember about the plane waves. If you want to write a wave going to the right, and you call right the positive direction, you should write it as kz minus omega t. If you want to go to the left, you should write it as kz plus omega t. And that gets us sort of all the rules to deal with plane waves, their intensity, and all that good stuff. Now, what we also need to talk about is what happens when we have sort of another extreme. So let's say we have this wave again. We're going to start it on a rope. And this time it's going to be connected not to a rigid wall, but rather to a ball bearing sleeve, if you will, that's nearly frictionless. So this thing right here can go up and down. If I send a wave down that, what's going to happen? Well, the wave is going to propagate this way, and then when it gets right here, it's going to lift this up. It will have, in fact, a little bit of resistance, but most of it's going to be non-resistance. So assuming again that it's well ball bearinged and greased and everything, so it's nice and smooth, then it will come back basically like this. You will have a wave that might be slightly smaller coming this way, but you'll also have a smaller wave upside down due to the little bit of friction you had. So this is what comes out of that scenario. Okay. So we saw that when it was rigid, we just got the upside down wave and it was about the same height as the incoming wave. In this case, it's a slightly lower energy. And of course, conservation of energy says it would be like 1 over a squared. So if I reduce this to 90%, then this would be related to it via the square. And this would be the square of this amplitude would have to be 10%. So that's how those two are related. Now, if you consider another scenario where, let's say you take a thin rope and you braid it to a thick rope, now you give this wave a little pulse. That pulse is going to continue to travel this way like this. And when it gets here, it's sort of like that because this rope is free to lift up and down, but this rope is kind of heavy. So what will happen is we'll get, after it hits that, we'll get now a little bit of wave coming back. Maybe it'll be slightly bigger than the one before, but it'll also have a wave propagating forward due to that mass. So it's sort of acting like this. It's going to continue going back in the upward direction, but it doesn't have to turn around because it's not a dead stop. So it's going to go this way. The part that's going to turn around is the part that was due to the inertia of the heavier rope. Okay, so that's really how these waves tend to behave. That is sort of a model for us to go forward when we're talking about waves running into conductors and insulators and stuff like that as well. So these are conceptual questions, again, that I've seen like on the MCAT and the equivalent sort of entrance test for law. So that's what they're talking about here. They talk about, these are reflections. This is a reflection. And this is a transmission. So when the wave goes from one medium to another, it's called transmitting. And when it's reflected, it's called reflection. And you can see that in section 15.7. That's basically it. The big thing to know also about waves, they talk about the standing waves and piano strings, first node, the first harmonic, all that good stuff. The other thing I want you to know is when a wave, it's kind of a neat thing. If a wave is coming towards another wave, like this, well, off the screen again. If a wave is coming towards another wave, their amplitudes just add point by point. So if I go over here and I try to draw exactly the same image here, and I try to draw exactly the same image here. Okay, what I do is I take this much and add it to this much, so I get there. I take this much and add it to this much, so I get it there. And then I add this much to this much, so I get it there. What you see is the sum of the amplitudes point by point, the sum at this point, the sum at this point, the sum at this point, and do all the points. That actually gives you the resultant of the wave. These two constructively interfered because their amplitudes were of the same side. They're both positive amplitudes. And then sometime later, oddly enough, it will look basically like this. The little wave is continuing on, and the other wave is continuing on as if nothing ever happened. So this is going forward in time this way, okay? So two waves coming towards each other. When they run into each other, the amplitude is just the sum of the amplitudes at each individual point. And then after they pass each other, it's like nothing ever happened. You can also have a wave that looks like this running into an identical wave that looks like this. And in that case, when they get right on top of each other, they'll completely cancel each other out. And then sometime later, it'll look like this and this, with this wave going this way and this wave going that way. It's okay, it's Mimi here, please. So you can see again, in this case, the two amplitudes were opposite. So you have what's called destructive interference. And in this case, you have somewhat constructive interference, but it's not exactly constructive. If the two waves were identical, it would make twice the amplitude. And that's sort of what we reserve for true constructive interference, but they're both interferences. So this is called interference. If you saw that episode of Big Bang Theory where Sheldon first goes to a movie in the series, I mean, it's not his first movie, obviously. He walks around the movie theater and goes, caw, caw, yep, yep. So he's trying to test the high frequency and the low frequency end of the sound spectrum at various locations in the theater. And basically, he's looking for areas where destructive interference would cancel out sounds. That would be a bad place from a movie standpoint, because some part of the spectrum you aren't going to be able to hear. So maybe you don't hear a person whispering, or maybe you can't hear the note of C or something like that. So he tries to go through all these different places in the theater and find out where his caw, caw comes back either amplified or at least the same, and whereas that deep noise comes back amplified or even similar. That's a sweet spot. That's all about interference, and that interference can be used really neatly. One of the tools that we use, or one of the things we use it as a tool for, is to find actual really small thicknesses. So you can imagine a little itty bitty, let's say it's a molecule. It's big for a molecule, but it's still pretty small compared to everyday things. And let's say we take a piece of glass and we tilt it on it like that. Now, what happens is it turns out light will come in and then it will transmit into the glass and will bounce back again at an angle. Notice this angle is different from this angle from the vertical. That's because of refraction. Light bending into another material is called refraction. Now, this is the actual ground. So some of this light is going to penetrate through and come back out at the same angle that it hit. And then it'll come back up this way. It'll switch again and go like this. Now, those two waves are so close together that they can either constructively interfere or destructively interfere. The main thing is if it comes out with one particular color being bright, let's say it's blue, then what you know is the blue wavelength, which might be around 350 nanometers, that constructively interfered. The only way you can get constructive interference is the distance, the extra travel time that it went, which is really this distance right here, which, you know, if this is the angle theta and this is the length L, you could say sine theta equals the thickness of that over hypotenuse. Well, the thickness of that is essentially due to the thickness of the difference in the path. So if that 2 times the diameter of that molecule, if that's equal to, in fact, 350 nanometers, then the blue will come out amplified. And therefore, you know that the thickness is on the order of 175 nanometers. So you can measure something really small, literally 175 nanometers, by just sitting up a piece of glass in this and watching how the light interferes with itself. If you get a strong blue line, that tells you that this extra path length, which is 1, 2, twice the diameter of this for small angles, then you know that path length difference is one whole wavelength, which is about 350 nanometers for blue. Therefore, you know that constructive interference just showed you this thing is 175 nanometers. it gets different. And that's actually, by the way, if you've ever been in a parking lot and you look down and you see a puddle and it's got that sort of rainbow on it, that rainbow I always thought of as like gas being in it. And some of it is petroleum issues, but really what's going on there is the puddle has different depths because the concrete isn't perfectly smooth. And the different depths allow different wavelengths of colors to reflect and interfere constructively and non-constructively. And these things change phases by a certain amount, and we know exactly that amount. So we can use this information to actually measure the thickness of very small things. But like I said, the one thing I didn't discuss is how the change of phase occurs when you go from here to here and from here to here and then back through here and then back through here. There is a change of phase that you got to reckon with. And I don't think your book covers it in this chapter. It covers it in a later chapter. Yeah, it doesn't cover it in this chapter. So we're not requiring you to do that. I was just giving you as an extra example of how you can actually use this interference property to make sense of those little wavy rainbows that you see in wet parking lots after it rains. And you can see that it can be used to measure small distances. The only thing your book does with reflection is it shows you that the angle of incidence is equal to the angle of reflection. And it also has Snell's law to some extent, but it doesn't really talk much about it. So you shouldn't expect very much with Snell's law, but Snell's law just tells you how an object, notice if it's reflecting, if it was 45 degrees from the vertical right here, then it would reflect out at 45 degrees from the vertical. But refraction is where it penetrates the surface of the glass. And that angle, if this angle was 45, the angle inside from the vertical between my fingernail, say, and that little line that's diagonal, that angle would be something less than 45. And that's called Snell's law. And it basically says N1 times the sine of theta 1. So that's the angle theta 1 that it made with the vertical outside of the glass is equal to N2 sine theta 2, where theta 2 is this angle. Okay, and I'm pointing to that little part right there, not to the part under here. Okay, this is the speed of light divided by the speed of light in glass. This one is the speed of light divided by the speed of light in air, which is essentially the 1 for air. So you don't really have to put in an N for that, but you certainly should put in an N for glass. And that allows you to figure out what the actual theta is for the second one. So that's really what they're doing. That's called Snell's law. And it actually can be derived by just assuming that light follows the path of least time. It turns out if you put a particle coming in at some angle like this and entering glass, and you said it's going to come out, say, here, and of course that's going to be exactly parallel to that. If you wanted to find the path that it would take, you could imagine all the individual paths that light could take to get here. And what you'd find is the path of least time is the one that gives you this equation. So that's a neat little sidebar. But I've covered all the major concepts here. I've given you the major formulas that are necessary. Your book doesn't even list Snell's law. It does it, but it uses the velocities. What I called C glass, it's just called in V2. And what I called C air, it's just called in V1. So it literally is using Snell's law, but it didn't actually call it Snell's law because that's introduced in optics. So you can now, with this material, you can make out everything that could be, all the equations that could be asked you of in chapter 15. And that's it. We're done. We're done with chapter 15. I'm probably going to use next meeting to just ask you guys to ask questions to prep for your final exam. If people come without questions, it's windy, buddy. If people come without questions, then I may lecture on elementary particles. But this stuff will be, as you can see, it's on the test that's already out there now. I've already put the test out there. And it's due, I think, April 5th. So this part's on the final, this part's on the test that I made available. But if I do elementary particles, I am not putting that on the test. So for next meeting, you're welcome to bring questions. I'm not going to count roll really, because it's really just a free session basically. And our exam is going to be, as I said, on the Thursday of next month, or excuse me, next week. Next month actually too as well. So that's when the exam's going to be. If someone really needs to take it on a Tuesday, you let me know. On the Tuesday, I'll get it done and have a version for you. So you also need to make sure that your Respondus lockdown browser is working and your Respondus monitor is working. You can look back at the test midterm to see if that's the case. If it is, then you're ready to go. If it isn't, then you're going to have to set up an appointment with the testing center to take your final exam in a face-to-face mode. Okay. Any questions? You're welcome to stick around. Otherwise, everyone is free to go.
Have an excellent day, Professor.
You too. Thank you.
Professor Younger, did you
Yes,
get
sir.
my email that I sent a couple days ago?
Yes, I did see an email. I don't remember what it was off the top of me, but I'm going to try to catch up today on emails. I got so many lately between that and trying to hire someone, a new hire. I just got behind. If you want to state it now, if it's public something, then that would be fine. Or you can just wait and I'll reply to it today.
No, yeah. It was about like the homework again. So like there were still like a bunch of homeworks that were labeled out.
I did remember that. I'm still working on that. I don't know what's going on, but evidently I'm going to have to do each individual assignment, even though it's supposed to fix all the assignments.
Okay. In my email, I just kind of like listed them out.
Late, right?
I did the one that was due yesterday.
Uh-huh.
And of course, like it was labeled at AM.
Oh yeah, gotcha. That's what it is. Okay, yeah, no problem. I'll fix that, and when I do, I'll let everybody know.
Okay, and I said in my email, I also listed out like the specific assignments that were due at the AM.
All right.
Okay.
Majority of the homework's supposed to be due like after the test. I mean, before the test.
You should always do the homework before the test. So if you're not, I'm just giving you extra points so you won't kill your grade. But it's insane to try to do them after. You really should be getting them done beforehand, because the whole purpose is to help you with the test. Obviously, it improves your score if you still do them afterwards, and that's why I'm throwing you a bone. But that's it.
Yeah, I'm just saying in order to study, because the test says due on May 3rd, but the homework is due on the 5th.
Yeah, it's just me giving you extra days, so I don't care about it giving you extra time on the homework. I would recommend you get it done before you take the test. Okay.
I'm saying, like, would the due date be for the test would be like after the due date of the homework?
No, the due date is the due date that I put on there, which I think was May 3rd. So that's what I mean. I've got the due date as the due date, and the homework due date is different, and they don't have to be on the same day or anything. So you're welcome to do it, but the due dates are at what they are. Does that make sense?
Yeah. And you say you're gonna fix the time error for chapter 11. Good.
Yeah. I'm glad you told me chapter 11. Yeah, I'm going to fix that one, and I'm going to make sure that all of them are giving you partial credit for late turn-ins. So, all right. All right, guys. We all have a good one. I'm going to go ahead and split. And
Professor?
Yes.
I have one quick question. I don't know if anyone else has mentioned it, but on the grades portion of Canvas, after I took the test, or the chapter 5 test, it's like lightly grayed out, and it says that the assignment is dropped and will not be considered in the total calculation.
What test was that you had taken?
Test 5.
Okay, I will look at that too. That's not supposed to be that way. So whatever happens, not right. So yeah, I'll check that out. But thank you for letting me know, Jasmine, and whatever's going on with that, I'll fix it.
Okay, thank you. Have a good day.
No problem. You too. All right, folks. Well, y'all have a good one.